already, I think we'll get started here. So thank you all for being here for the last iteration of the data-driven seminar series this term. And we have the pleasure from hearing from Enrico Camporeale here from Queen Mary and University of Colorado. And we're excited to hear about machine learning for space weather and the challenges for air and extreme events.
All right. Well, thanks. Thanks everybody. Thanks for the kind invitation. It's really nice to be here. It's actually my first time in Seattle, so I really enjoy the weather. It's what it is, but I came from London, so we're talking about being very, very similar indeed. So this is not my usual audience, as you probably know. My usual friendly audience. I'm sure you're friendly, but it's not my usual audience. So what I was thinking to do is to, obviously I'm going to talk about machine learning for space weather, kind of assume that maybe you're not very familiar with space weather, so I'm going to spend a few minutes just to introduce the concept and see why we are interested in studying space weather. Then I'm going to pivot more into kind of showing you what are the challenges in using machine learning for space weather, hoping that maybe some of those challenges will resonate with the things that you do in your particular applications. And then I'm going to go more into the algorithms and more methodological into the problem of rare and extreme events. So I always thought that for people that do not work in space physics or space weather, a good way of getting excited about space weather is to watch some videos. We have plenty of those kind of videos. You can spend hours on the NASA or ESA website watching videos if you like them. So what is gonna, let's see if this plays first of all. Yeah. So what is gonna be shown here? So this is a ESA instrument, ESA satellite. So this is only a 1 day of video. You might know that the sun takes 27 days to do a full rotation. So in 1 day, you just only notice a very small rotation. What is shown there in the red arrow is what we call a coronal mass ejection. So it's a large burst of plasma that comes out from the sun. So what we're going to see in a minute is this coronal mass ejection. As I was saying, it's a kind of change in the topology of the magnetic field that gives rise to this burst of a bubble of plasma. And then this is actually a composite video taken from different cameras. You don't see much when you look up close. Then if you kind of zoom out, you can see this kind of something coming out. And then when you have a very large angle, you can have a kind of better understanding of how big this stuff is. And I mean, compared to the size of the sun, and then you can think about compared to the size of Earth. This is obviously a lateral view of what 2012, and this is a NASA satellite called Stereo that happened to be kind of in the line of fire of these events. And you can see, again, this obviously runs very fast. It's several hours. The CME explodes, and then you have this, what we call kind of a snowflake effect when these charge particles, electrons and ions hit the camera and they kind of saturate the LCD. So you might wonder, what happens if Earth is in the line of fire, and this is, generally speaking, the field of space weather. It's kind of an umbrella term. This is a slide that we use a lot. It's kind of a lot of information. Most of it you can't even read it, but essentially there are three things we are interested in studying space weather when it comes to the effect of this sun, solar dynamics to Earth. So one is the coronal mass ejection, which I just mentioned. This is literally a bubble of plasma coming out. It takes about 2 to 3 days, depending on the speed, to reach Earth. Then there are solar flares, which is a completely different beast. Those are X-rays. So they travel at the speed of light. They only takes 8 minutes to reach our atmosphere. And then on top of this, there's a continuous flow of of charged electrons and ions that we call the solar wind. This flows continuously, and once in a while, the speed and the pressure gets higher, and this can cause some space weather effects. So I don't know if you can see it. It's not very clear. It's kind of pixelated here, but this is Earth. You probably know that we have our own magnetic field, the Earth's magnetic field, which is generated by complex dynamo processes in the core of the planet. And this is so the fact that we have a magnetic field is the reason why life can exist, right? So we are protected by this effect. But once in a while, when these effects happen, basically there is a strong shaking of the magnetic field. And so there's space weather is kind of a curiosity-driven science in a sense, but has also important societal effects and economic impact, as you can imagine. This is another kind of very used or abused slide in my community, where you can see all kind of effects of these space weather events on, well, it's not very hard to imagine. You know, a satellite can be knocked down or damaged by energetic electrons or ions. There can be radiation on polar orbits, especially. So there's an effect on avionics, GPS scintillation, all the way to the ground. You might remember from your Physics 101, Faraday's law. Every time you have a shaking magnetic field, you have an induced electric field. And if the electric field is kind of aligned to a conductor, like a power line, you can have an extra current. And it did happen. It's not very frequent, but it did happen that blackout occurred because this extra current went into a power station and burned a transformer. This happened. I mean, the most famous example was in 89 in Quebec. And then on top of this, of course, the kind of the final product of space weather are auroras and northern lights. I believe probably here in Seattle we are high enough latitude that you can see northern lights. Maybe not in the city; you have to go a bit outside from the city lights. And this is when basically energetic particles following the Earth magnetic field precipitate into the atmosphere, collide with the neutrals, and make light. So keep pressing this, but. Many in the community think that space weather is kind of a disaster waiting to happen, and this is why we're interested, again, from the economic and societal point of view. Now, it's very hard to make estimates of the economic impacts. These numbers are, I mean, this is really not my field. There's people working in economics trying to understand, you know, the cascade of events that can cause so much damage economically. Financial market blackouts and so on, satellites. So the numbers are not really, I mean, you can take with a grain of salt. I mean, we're talking about 100 millions to a few billions. An interesting point to make is that ESA is projecting that by 2030, there will be around 100,000 satellites orbiting Earth. You might have followed the news that Starlink, Amazon, and so on, we really have an exponential increase of satellites, especially in low Earth orbit. Again, another projection says that the overall space economy is supposed to reach some $1 trillion by 2035. So there's a lot of money, a lot of interest, and we want to avoid these economic impacts. In a sense, I like to see space weather as a black swan. You might be familiar. This was a popular book that kind of popularized the idea of a black swan. Black swan is an event which is, in some sense, changes somewhat the course of history and humankind. The characteristic of a black swan is that it's very easy to understand what happened after it happened, but it was very hard to predict it when it happened. And classical examples are, COVID, 9/11, this kind of stuff. There are also positive black swan events, like the invention of the press, for instance. So the things that change the way we live. And so people, including myself, believe that if a big event might happen, this might actually be a black swan for the Earth, for the human kind of economy and where we live. So the idea for space weather forecaster is to, or modelers like myself, is to get to come up with some models so that we are able to forecast to some extent some of these events, so that we are not in the situation like the bunny in the book of bunny suicides. We just sit and wait for the disaster to happen. This is, again, it's kind of resolution is not very great, but this is a great book that I recommend, especially for grad students, to save a lot of money, therapy, and things like that. Anyway, so changing gears a little bit. So you might wonder, how much has been done? I mean, obviously you're aware that machine learning now has been used pretty much in every fields of natural sciences, physics, geophysics, and so on. And the same happened in heliophysics. So I would say I've been working in this field now for about 10 years. And in the last 10 years, machine learning has literally been applied to any possible problems that you could think of with some data, some inputs and some outputs, sometimes in a good way, sometimes in a not so smart way. And typically when you see a paper of machine learning so heliophysics, kind of the broader field of where space weather lives, typically a machine learning algorithm claims to be outperforming the physics-based equivalent. So this is a community, a physics community that is very much grown with, doing large-scale physics simulation. So that's our kind of baseline. It's also fair to say that most of the time these baselines are not very strong, so it's not very hard to beat them with a data-driven method. So I just want to mention, so again, it's a field which is growing. So we just held a few months back the third conference of machine learning in heliophysics in Spain. So my kind of guesstimate, you might be familiar with this curve of innovation, where there's some initial innovators, some early adapters, and slowly pretty much all the community starts to embrace a new technology. I would say that at this point, maybe in heliophysics, we are somewhere here. So I would say, 20-25% of the community is very well engaged with machine learning, and the rest is divided between skepticals and people that know that they should learn it, but they don't have the time, and so on. So it's still kind of an early stage, but a lot has been done. So I don't particularly like to promote myself in this way, but this is a review paper which has happened to be very highly cited in the community, which I wrote back in 2019. I was asked by AGU, the American Geophysical Union, to write. So at that time, there was already enough literature to put together a long and boring review for the community, especially for students and early career people. So I did that. And then on top of that, I thought, okay, this is a very boring reading, as all the reviews are, very long, like 300 citations, 300 references, and so on. Then the very last sort of section or paragraphs, I thought, okay, let's sit down and think about challenges that might be interesting for the space weather community or the heliophysics community in general, that the community should overcome if we want machine learning to succeed in this field. And then recently I looked at this paper. I think it's a good exercise for every scientist, maybe every 5 or 10 years, to sit down and look where we were 10 years ago and see what has been done. And again, a lot has been done, but I would argue that these 6 challenges are still very much open. So now what I'm going to do is, so there are 6 of those. I'm going to go fairly quickly through the first 4 with the hope that maybe some of these, again, will resonate with some of the problems you see in your own application. And then the focus of the talk really is on the last 2, the rare extreme events and the UQ. So the first one, which to me really is it's probably the biggest and hardest challenge, and what has hindered the progress so far, not progress in the sense that progress has been done, but has hindered breakthroughs, maybe it's a better way of saying it, is the information problem that in machine learning jargon would be the feature extraction. The reason is that, we believe that obviously the sun is the driver of all space weather events. So if any information we should use is the information coming directly from the sun. And thanks to this is a NASA satellite, images from a NASA satellite called SDO, the Solar Dynamic Observatories. So that satellite takes these are pictures of the sun at different wavelengths every 12 seconds at high resolution. This is 4K by 4K. So in total, at any given time, we have about 200 million pixels of information that we can harvest. Now, the problem really is how to funnel this information into knowledge, right? Because for instance, for a space weather forecasting problem, you might want to be able to output or to forecast only a few scalar outputs in the future, like solar wind speed, temperature, density, and so on. So this really is a feature extraction problem. We have this huge amount of data in the sense of really 200 million numbers. And again, the assumption must be that the information is there. And I do believe that the information is there, but how to extract that is not clear. And, the community has tried, as we do, has tried all the classical machine learning machineries, convolutional neural networks, vision transformer. And then again, they work to some extent, but I really do believe that for this kind of problem, maybe if we want to tackle by machine learning, maybe we need to come up with a new architecture which is designed explicitly for this problem. But obviously, the easiest thing is to take stuff off the shelf like CNN and things like that. The second problem is the gray box problem. You might be familiar with this figure in a paper by Karnadakis et al., where basically you have to decide where you live in a spectrum between lots of data and very little physics and very little data and lots of physics. And the gray box idea is to live somewhere in between, which I think is the winning idea in the sense that in any field of physics, there's 50 plus years of knowledge, and we do want to know that we do want to use the knowledge somehow embedded in our data-driven models. And I mean, the gray box approach doesn't need to be particularly sophisticated. So this is an example of a paper that I published a few years back where we try to enhance a physics-based model for a particular space weather forecast. And what we did literally just to take the output of a physics-based simulation and use those as features, as input of a machine learning model. And we showed in the paper that approach, as simple as it is, actually had the best performance compared to a purely data-driven model or a purely physics-based model. It was living in between and was getting the best of the two. The third problem is the surrogate problem. So space weather is often seen as a chain of events, starting from the sun, the solar wind propagation, the effects on Earth and the magnetosphere. And typically these problems are treated kind of separately, and then you try to couple in a chain, as in a chain, all different models. And then the question is, as I said, typically these have been treated so far in the community by either empirical or physics-based model. And obviously, if you can create a surrogate of any of these links in your chain that is machine learning or data-driven, obviously we all know that would be much faster, but there's a trade-off between accuracy and computational efficiency. This is a work done by a postdoc at UC Boulder, Pratik Mayank. Is going to present this next week at the AGU meeting. Again, I'm sorry that the resolution is really bad on these slides, but essentially what it's building on is a surrogate of a 3D MHD model. And this is something that the community has been talking about for a while, but I don't think anybody has done it yet. And I was actually surprised to see how not easy the problem is. I was thinking that, at least ideal MHD would be easy enough to replicate as a surrogate model. It's using a physics-informed neural operator, and those are preliminary results, but it looks like we're getting there slowly. The fourth problem, which is maybe the problem that is most interesting if you come from a physics background, is the knowledge discovery problem. So at the end of the day, if you talk with the physicists, they don't really care about how accurate your model is. They want to understand what new physics you discover. And this is, so how do you, in a sense, distill some knowledge from a machine learning model and how you improve your understanding of a given system? So I mean, this kind of aligns a lot with, I believe, some of the work that has been done here in the terms of PDE discovery from the data and so on. The paper I show here, it's actually an archive paper that was never published in this current form. We have to massage it a little bit to make it more acceptable by reviewers and so on. But the idea here, okay, I'm not going to get into the details. So this is solving an inverse problem for the transport of electrons in the radiation belt, where the typical paradigm is to use a Fokker-Planck equation of a diffusive form. So this the standard model in 50 years of literature will be to use a diffusive equation like these first two terms. And what we did, in this case using PIN, physics-informed neural networks, is to say, okay, let's see if we add a missing term here, some missing physics, and the PIN is able, obviously, to estimate the diffusion and the drift coefficient. And we show that by enhancing the model in a kind of a data-driven way, this more complete model matches with observation, with data much better than the standard only diffusive model. So in a sense, this is what I see as a knowledge discovery with discovered there was some missing physics, which obviously is interpretable because this is an operator that we know how it works and what it means physically. Okay, so as I was mentioning, the last two, and I'm going to dig more into these into these two problems, is the uncertainty problem. So I, like many other in the community, kind of subscribe to the school that the forecast is not a forecast if it's not probabilistic. Now, many people doing machine learning are happy just to spit out a single number as your forecast. That is not very actionable, let's say, if you don't estimate the uncertainty that comes with it. And the last one is what in that paper I call the too often too quiet problem. The technical term would be imbalanced regression. So oftentimes we deal with the regression problems where we want to forecast a scalar number, but the data set is very, the distribution is extremely skewed. In fact, the interesting events oftentimes are smaller than 1% of the data set. And this is very challenging if you do sort of vanilla machine learning where you use your mean square error in your cost function, because all the interesting events will be completely hidden in your cost function. So you need to come up with some other ideas. All right, so digging more into the first problem, the UQ. So I'm going to talk briefly about this method or model, which is called ACRU. It stands for Accurate and Reliable Uncertainty Estimate. I'm going to give you the reference in a minute. Essentially, the question we try to answer in this work is how to estimate the uncertainty of the deterministic model. And I mean, this is now, I don't know, 5 or 6 years old. When I started working on this, in the back of my mind, I had, again, coming from that community, I had the idea that the deterministic model would be a very expensive physics, maybe a legacy code, very expensive 3D MHD model, and so on. So the idea is that you don't want to change the underlying deterministic model, because that's as good as it is in a sense. But what you want to do is to use that model as a mean of a distribution, and you want to estimate the uncertainty, the standard deviation of the distribution. And the first step is, I'm going to get there in a second, is to obviously work with Gaussian distribution, which is not very realistic, but we're worked on an extension of that as well. Now, it turns out that actually this method is kind of model agnostic. So again, I had in the back of my mind physics-based simulation, but this applies just as well, as long as you have a deterministic model. It can be machine learning, can be empirical, and so on. So obviously, this is just for visualization. It's a very simplified view, but essentially, if you have your input, which typically is multidimensional, but in this case, it's just 1D, and your model gives you a function of f of x, which is this red line. Obviously, the model is not perfect, meaning that when you look at data, there's a distribution of the data. So what you want to do is to be able to estimate sort of a posteriori the confidence interval. The technical term, kind of funny name for this, it's the heteroscedastic uncertainty, meaning that you can see the uncertainty is input dependent. So it might be very small here, very large here, and so on. That's what heteroscedastic means. So this is the setup. Again, given a deterministic model that produces scalar output for a given input, again, my input can be multidimensional, very complex, and so on, but the crucial thing is that every time I feed the same input to the model is completely deterministic, always gives me the same output, right? And I call this output mu for obvious reasons, because I'm going to use this as a mean of a distribution. And then obviously you need to have some true values or some ground truth that in this case I assume are noiseless observations. This might not be true as well. So what we want to do is to produce a probabilistic forecast in terms of a Gaussian probability. So I take this mu and I literally put a Gaussian on top of it. And so all that needs to be estimated is the variance or the standard deviation. So the question is, how do we define the optimal variance? And it turns out that for a probabilistic forecast, there are many things you want to do, but to the very least, you want to ensure that there are two characteristics of your probabilistic forecast. One is to be accurate, and the other is to be reliable. And I'm going to explain what those terms mean in a second. Well, accurate is pretty obvious to understand what it means. The thing is that if you look in the literature, especially the atmospheric weather meteorology literature, there are many metrics you can use for estimating accuracy. what we decided to use is something called the continuous rank probability score, which again, it's valid for probabilistic forecasts of continuous variables. What I like about this is that it's very easy to understand graphically. I mean, this is the formula, just an integral, but I'm gonna get there in a moment. So again, we're working in a context where my forecast is a PDF, right? And it's a Gaussian. So assume that this red line is your forecast for a given event. And then you look at the observation, and the observation is only one given scalar value. Now, if you look at this in the CDF space, in the cumulative distribution function, the red Gaussian becomes this kind of sigmoid function here, the red line. And you can associate with your single scalar value a step side function, a heavy side function, right? So essentially, the CRPS is just the area between the two square, right? So it's the integral between the differences of the difference of the CDFs. So it's very intuitive in the sense that obviously when this area goes to 0, it means that your forecast is exact. You know, it means that the sigma, the standard deviation of your forecast, got to 0, and the mean got exactly on the observation. So a nice property is that this CRPS actually becomes the mean absolute error where sigma tends to 0. So it's a negatively oriented score. You know, the smaller, the better. Reliability is a different beast. You can only define reliability not for a single observation. It's more of a statistical property of a model. And it's the property of a probabilistic model that measures the statistical consistency with observation. So again, a good way of understanding this is visually with what is called the reliability diagram. So say that every time your model predicts 40% chances of something, like 40% chance of rain, if you take all the time that you predict 40% and it actually rains 60% of the time, it means that you're underconfident, right? The other way around, if you predict 40%, it only rains 20% of the time, you're overconfident. So the reliability diagram, basically the optimal reliability, is when you sit on the diagonal line. And especially for Gaussian distributions, I'm not going to show the math, but there is a simple way to derive a cost function like a reliability score, which is analytic, closed form and differentiable, that you can measure the reliability. Now, the interesting thing is in this context, I mean, you can probably, if you come more from statistics, you can see this. It's simply a likelihood estimation problem in a sense. You want to understand what's the likelihood of your Gaussian distribution and minimize the log likelihood, maybe. But in the framework where you take, I mean, you don't have much choice in the mean of the distribution, meaning that the mean comes from this underlying deterministic model, and you only are trying to optimize the standard deviation or the variance. It turns out, and this is very interesting, that the accuracy and reliability are competing objectives. So this turns into a two-objective optimization problem. And this is a graphical example to show this. Okay, here this is taken from a paper where instead of CRPS, here I use the negative log probability density of the negative log likelihood, but it works just the same. So what is shown on the left here are two different models. So this is just to make the point that you can have two different models. One, the blue one has a perfect reliability, and the red one is obviously not so good in terms of reliability, but they have the exact same accuracy score. And the other way around, here you have different lines with the score going lower and lower, so the accuracy gets better and better, but the reliability gets worse and worse. So again, this is a two-objective optimization problem because CRPS or accuracy and RS or reliability score are competing. So a simple way to deal with two-objective optimization is just to linearize your score, meaning that you just take the sum maybe with a weighting factor in between. Again, the crucial point is that these two scores individually cannot be minimized simultaneously. So we have to find the best trade-off. So the idea, I'm not going to show the algorithm, but it's very simple. The idea behind accrue is to minimize this composite score. There are a number of ways of solving a minimization problem. And we found out that especially if your input is multidimensional, you can just use a neural network to minimize that, and this works fairly well. So these are the papers. One is the kind of original one published in the International Journal of UQ, where we introduced the model. Then we showed an example of how using this model for some space weather prediction. This is just an example of, we took a neural network developed by a different group, actually, that does some forecasts of radiation belt electrons, and we just plugged on top of it these accrue methods to estimate the uncertainty. So it's not very easy to see, but basically the contour line here are the uncertainty for different times. The nice thing about this is that contrary to, there are many ways of dealing with uncertainties. There are some machine learning methods that have some sort of built-in UQ, but typically, especially from a physics perspective, the way to deal with that is just to run ensembles, change the boundary condition or whatnot, and this is very expensive. So the nice thing about this is that you don't need to run ensemble as long as you have a large enough data set of ground truth and observations. It's kind of plug and play, model agnostic, and the code is available on that website. All right. I'm going to jump to the second problem, which is, again, the too often too quiet problem. I'm going to show two algorithms or methodologies to deal with that. One is more mature. The other is still pretty much a work in progress. But I'd like to maybe to hear your background, your feedback about that. So again, I believe, this is very much true in space weather, but I believe this is true in many environmental sciences or geophysics application or even engineering, where the data set is so imbalanced that you can't just throw a standard machine learning method to it. So just to have a kind of an idea what we're dealing with, I made some example here. So when we talk about solar flare predictions, if you take the days without a flare versus the day with the other way around, the days with a flare or the days without, there's a factor of 40. So 40 times the days without flare are 40 times more abundant than the days with. The playground we often use in space weather is to try to predict the geometric index, which is called DST, stands for disturbance storm time. You can think of this as just a single scalar number that gives you it's a proxy for how strong a geometric storm is. So you can think of an analog of the indices we use for earthquakes or things like that. And the way this is defined, it's in nanotesla as physical units. And when there's a strong storm, this goes very largely negative. And if you look at the data set, only 0.7% of the time this goes below minus 100, 0.07 below minus 200, and so on. In fact, I think I have a CDF of DST. This is the cumulative distribution function. And again, the interesting events when there's a storm, it's when this goes below minus 100 nanotesla. And you can already see from the figure, these are almost invisible here because it's less than 1% of the events. This makes it very, very hard to predict. Now, the typical approaches to imbalance regression, the literature is not huge about imbalance regression, but there are some methods, obviously. Typically, there are two strategies. One is to resample. This has been done more in the context of classification rather than regression, but the idea is it's very similar. You can either oversample the rare events, so you have more rare events, and so that the balance gets a bit better. Or you can undersample the frequent ones. There are some methods like this SMOT, which is pretty popular, where you do synthetic data generation of the minority class. So you create more data of the minority class so that it becomes less imbalanced. Another way, which is even simpler, is just to reweight your loss function. So if you take a standard mean square error, every single sample is counted the same, but obviously if you put a weight factor in front of some samples, give you some more weight to the rare events, this should in principle take care of it. And typically you can use, there are different weighting schemes, but just taking the inverse frequency or the inverse CDF works. Now, what I'm going to propose here is yet a different approach which we create some ensembles which are uncertainty aware. I'm going to explain in a moment how this works. Unfortunately, so we call this ProBoost, probabilistic boosting, because it's basically it's based on the idea of gradient boosting, although it's a bit different. It's been inspired by gradient boosting. We didn't, unfortunately, we didn't publish a paper specifically on the method, so the method is kind of hidden in this space weather paper, and therefore maybe it's not so has not become so popular or widely used. Also, we kind of realized, looking at the literature, we kind of messed up because we call the method ProBoost in the paper, but we use the word multi-fidelity boosted neural networks in the title, so we kind of messed up with naming a new method. But anyway, let me step back for a second. I mean, I presume most of you are familiar with gradient boosting, but it's good to summarize how this works because, again, ProBoost has been inspired by gradient boosting. So gradient boosting is one of the most powerful methods. If you look at machine learning competition, Kaggle, that kind of things, like 95% of the times, gradient boosting is the one that wins. And it's a very simple and powerful idea. It's based on creating kind of a hierarchy of models. So assume you want to solve a regression problem and you train a first kind of baseline model. It can be a decision tree, a neural network, whatever. Obviously, the model is not perfect, so you train your model, and then you can calculate the residuals of your model on your training set. And then the very simple idea, you can take those residuals and train a second model on top of it, where the residuals are the target, and you can play this game a number of times. And at the end, you have n kind of sub-models that are additive. You can just add them all together, and the prediction is much better than any single model, right? Again, very simple and strong idea. Unfortunately, it underperforms for imbalanced dataset for obvious reasons. What I'm showing here in blue, this is the ground truth for this DST index I was talking about. And as I was saying, during the storm, this goes very negative, down to minus 400. Now, if you apply gradient boosting here, you can see that gradient boosting is very good at predicting everything except the storm, right? And this is our problem, and we're interested pretty much only in the storm. So we thought about a way of also creating an ensemble of models and putting them together. But the key point is how do we train those? We were thinking maybe we can use a crew on each one of these models to identify in feature space where the uncertainty is larger and where it is smaller, right? And therefore, you can subsample your training set. So the second model will be trained only on a smaller region of your original training set, so that the second model focuses on regions where the first model uncertainty was large. And again, you can play this a number of times. And then because each member of the ensemble is uncertainty aware, meaning that it comes with its own estimate of the uncertainty, you can use their precision, which is just the inverse of the uncertainty, as the weight when you put them all together in a linear fashion. Again, it doesn't unfortunately show very well here, but what is shown, it's kind of a toy example here, but assume that the blue, this again DST, the blue line is your target, your ground truth, and here we have two models. So one, which is the red one, it's simply a persistence model, so it just kind of shifts by 1 hour your prediction. And the yellow one is a neural network. And so these dots here, the size of the dots are the uncertainty of that model at that given time. And if you combine the two models, again, weighted by their precision, what comes out, it's really hard to see here, but there are these diamonds, which are kind of the best of the two. And so we have used this ProBoost strategy, again, in that paper. And then this is a model called LiveDST, which runs 24/6, kind of operational model that is running on a website at the University of Colorado. Okay, this particular case is not so interesting, but basically this is a model that makes prediction of DST 6 hours in the future with its own, you can see this shaded area. So this is the forecast with the shaded area, which is the uncertainty. All right, how are we doing? Time. Okay, the last kind of 10 minutes, I want to dig more into this idea of dealing with imbalanced data set. And this is a new algorithm which I've been working on for the last several weeks. So there's a paper now on the archive I'm gonna show you in a minute. And that is kind of similar to ProBoost, but kind of different in the sense that what we want to do now is to prune our data set. Now, pruning has different meanings in machine learning jargon. Typically, lots of literature looks at pruning. What it means is to prune your architecture. So take a very complex architecture and find maybe a subset of that architecture that has equal performance. And there are some very interesting papers that show that you can do that. What I mean here by pruning is rather to reduce your data set, your training set. And this kind of goes against the current narrative in some deep learning communities where now foundational models are very popular. What I was showing here were a couple of things. So this is a paper that made exactly that point. Do we need more data or do we need just better data? Of course, this is very much problem dependent. What I'm showing here, it's a news that came out a few weeks or a few months ago where IBM and NASA kind of partnered together to make, for the space weather problem or the heliophysics problem, they made a foundational model based on solar images. This is just to give you an idea how big this is. So they had to train on 257 terabytes of data to come up with this foundational model. My point here being that, again, 99% of the data, it's quiet time. So it doesn't really help you to predict solar storms. Okay, to explain, and by the way, the algorithm is called Paris. It's a brilliant acronym that ChatGPT came up with. It's called pruning algorithm via the representative theorem for imbalanced scenarios. So to explain that, I need to explain a little bit what the representative theorem is. You might be very familiar with this. I have to admit, I only discovered, I don't come from statistics or machine learning, so embarrassingly enough, I discovered this only a few months back, but I realized it's very standard knowledge. So when you apply the representative theorem to neural networks, this is how it works. So if you take pretty much any neural network, you can always think of it as, no matter how deep it is, how complex, what kind of architecture, whether it's transformers or whatnot, you can think of this as a number of layers. And if you look at the penultimate layer, this is basically your feature extractor, your encoder. And you can always, and this is actually what is done typically, especially in the context of regression, where your output needs to live on the real axis. You have a last layer, which is just a linear layer. So you basically, all these features here, they are kind of projected into a single scalar output through a simple linear layer, right? So if you look at the neural network in this way, you can rewrite your output of your neural network, f of x, simply as, so phi of x here will be the penultimate layer, your feature extractor, times w. So this is just a linear regression, right? When then you can create a matrix where each line is a vector phi. So just for kind of bit of nomenclature, D here would be the dimensionality of your encoder, so your latent space dimension, which depending on the problem is typically 50, 100, 1,000, and so on. N is the number of training points. This is much larger than D, right? So I'm not going to show you the algebra, although it's all very simple. It's all linear algebra, very straightforward. But basically what the representative theorem tells you is that when you apply your neural network to a new test point, to any point really, you can write the outcome of the neural network as a sum of dot products between the feature vector applied on the test point times the feature vector applied on the train point, rescaled by a scalar number, okay? Now, when I looked at this, I literally, again, embarrassingly enough, I didn't know about this, but, maybe coming from a physics background, I was very surprised because, physicists love to project everything onto a basis function. And this is exactly what it is, right? So basically this phi of x, which is the vector of your latent feature, is the learned base, is the basis that the neural network has learned through looking through the data, right? And this is also very, this is all you need really if you want to come up with a pruning strategy, because this immediately tells you that if you have any vector phi of x test, which is orthogonal to phi of x train, means that that single training point does not contribute to the output of the test point. And that's all you need for pruning, right? And this is exactly what we did. There's a bit of math here, it doesn't really matter, but essentially we build a matrix, what we call the representative influence matrix, where every row is a different point in your validation or test set, and every column is a point in your training set. And basically, to get the final output for a given, again, test or validation, you just sum over all the columns of this matrix, right? So it's just basically just this summation here. Again, this immediately gives you a pruning strategy, because what it means is that if you now take away 1 point from your training, you are just zeroing out the column of this matrix S, right? So the criterion we use is to say, okay, let's see, now you have a loss function, which is mean square error. If we take out 1 point from the training set, how does that loss changes? And this is what this delta L, it's a bit of an language. So this delta L kind of slash K means, when you take out the point xk, this is evaluated on a single point V star. This is, again, it's a closed formula. You can do this immediately. And the idea, kind of the assumption, the big assumption, if you like, is that, if you have a trained neural network and you're just removing 1 point from your training set, you don't really need to retrain the neural network. I mean, it's going to be pretty much the same, right? Obviously, you can play this game a number of times until you do need to retrain. And I haven't really explored all the parameters, but what I'm going to show you in a minute is an example where I remove up to 5% of my training point size. And then after I remove 5%, I retrain, because at that point I think, okay, maybe the features need to be kind of updated. Now, the interesting point, again, I played this game with this problem of predicting DST, and I went all the way to pruning 75% of my, so this is we're talking about a data set of about 20,000 samples, so it's not huge, but not small either. So I reduced this data set all the way to 25% of the initial size. And what is shown here is the following. I'm going to try to explain these figures carefully. So again, if you look at the mean square error, that's not the metric you want to look at, because the mean square error kind of averages everything equally. So what is shown here is a conditional RMSE. So the Paris model is this blue line here on the bottom, and I compare with other different baseline. So what's called baseline here is just a standard neural network without doing anything. And then there are different ways like focal, density weight, and so on. And what is shown in the plot is again a conditional RMSE, meaning that for any given value of DST on the bottom, I calculate the RMSE only on the samples for which the ground truth is smaller than that value. So it's kind of a condition RMSE on the ground truth value. And you can see, again, being on the bottom of all the other lines, that the Paris method outperforms everything. Again, if you look at the last number here on the right, this would be the standard MSE computed on the whole training set. On the whole test set. Another way of looking at this is if I compute the RMSE on different percentiles. So if you take the smallest 1% of points in my test set, and I compute the RMSE only on the smallest 1%, you can see that the RMSE is about 75, so outperforms all of them. And it's still, it's good up to a point where maybe up to 15%. And then it's still good in a sense that it's very similar to other methods, but it's not the best. And again, the crucial point to emphasize here is that all of these results are based on a training set, which is 25% of what has been used in the other methods. So really, the idea is to find the minimal but most informative training set for this particular problem. So there's an archive paper which I managed to put online a few days ago, just because because I have a poster about this next week at AGU, so it was good to have something online. And so I'm going to get into my conclusions. So ML in heliophysics is a rapidly growing field. There are there's a few challenges to be solved, at least 6. Those are the one I mentioned in my paper. And what I showed in this talk in particular are the challenges of UQ, so quantifying uncertainty on top of a deterministic model, and this very hard problem of imbalance regression. I showed in particular 3 different methods. So accrue is a post hoc or a posteriori algorithm for uncertainty estimate, where you have a deterministic model, you can just plug it in what is the optimal uncertainty. ProBoost is a strategy that uses accrue sort of to train submodels, train on different regions of your training set. And finally, Paris is this pruning algorithm that seems to work very well for imbalance regression. Last 30 seconds before I finish, one can advertise a new, I don't know how many of you actually work in fields related to geophysics, but there's a new journal in the family of JGR, Journal of Geophysical Research, by AGU, which is called Machine Learning and Computation. I'm the editor-in-chief, so if you're interested in publishing in that journal, you can have a chat with me. Thanks very much for your time.
All right, we have a few minutes for questions. Any from the room?
So I got the approach of pruning for the imbalance regression. I was wondering why you chose pruning using representative theorem rather than something like setting your weights on a weighted MSE with the representative theorem. Or are they almost the same effectively?
It's a good question. Well, if you prune, I mean, obviously there's the overhead of pruning itself, but the idea is that if you then come up with a minimal data set, obviously all later training are going to be cheaper, right? Because and then maybe, I mean, there are different ideas, and I'm hoping to have the time to look into in the future, is also maybe to learn some physics, because, this data set, this prune data set is really where the information is in regarding to the imbalance regression problem. So, why is this one sample more important than the other? And so that really gives me the information I can dig into. But yeah, I mean, maybe from an algorithmic perspective, it might be similar to just reweighting with those. But then, I mean, the problem with reweighting is that you need to find the weight, and there's not a simple. So pruning is pruning. I mean, once you take out one sample, that's all you need to do. Reweighting, you need to find a function that gives what's the importance of each sample. So it's more complicated, I think.
Okay, so you think maybe representative theorem wouldn't be a good way to tackle weighting, or at least not.
Well, I don't know. It might be. I don't know if maybe it's been done already. I'm not so familiar with the literature.
Thanks.
Other questions from the room?
So I'm thinking of applying some of these ideas maybe in, you put a hydrophone in the middle of the ocean, you listen for a year or something like that, and it's a lot of data intense. It's very data intense.
Mm-hmm.
What scalar data, pressure or something like that, on a single sensor, one time series. Mm-hmm. What is the nature? Could you explain the nature of the data, the raw data you work with? You showed pictures.
Yeah.
Is it a time series of what?
Yeah, so in this case, for the DST, I didn't really talk about that. It's time series. So we have 2 ways of doing space weather prediction. So one is using those images I was talking about, remote sensing, but this is not what that is. So we have in situ data from some satellites of what is called the Lagrange 1 point, which is a stable point that close to Earth, and we have in situ plasma, so that those satellites measure the solar wind speed, the magnetic field, and so on. So this model for forecasting DST use, so this is why it's kind of a short-term forecast. It only goes a few hours ahead. It takes plasma density, speed, the magnetic field, the three components, and so on. So it's about 5 or 6 scalar value. It takes the time history of this, maybe 6-7 hours. So all in all, it's like 50 features, but it's all tabular, it's all time series. So I guess in that sense, it's similar to what you're talking about. And then it also, because DST is a strong autocorrelation, it might also use the value of DST, value of the target in the past, because it's strongly correlated in the future. And then you just spit out one single scalar output.
We have a question from Zoom, which is, have there been many studies into synthetic data generation for something like solar flare prediction?
No. Well, there are some papers. This is where the community is really kind of divided. There are some papers that use some generative AI to produce images of the sun, like magnetograms and so on. Now, the problem with this approach is that the images might look, it's not like when you generate, I don't know, an image of a cat, which it looks like a cat, it's a cat, yeah, sure. When you generate something which has a physics background, you don't know whether that's actually something that can happen in reality or not. So there's no ground truth, obviously, because it's generative, and there's no way of checking whether those synthetic images might actually help with prediction or not. But yeah, there are a few papers that have done that.
I have a sort of philosophical question. Very early on, you said that a lot of the in this field, one of the classic things to do is show that some ML algorithm outperforms a baseline. And then you mentioned that those baselines are often quite weak baselines. And I think in a lot of fields that people in this room work with, those weak baselines can sort of come from two different points. One is there might just be, it's very difficult to come up with a baseline in the first place. And the other might be that it's advantageous to choose a weak baseline to compare to. And I wonder if you have any comments about the prevalence of both of those sets of weak baselines in the field.
Yeah, I think obviously both of these things can happen. I think particularly for space weather, space physics, as I was mentioning at the beginning, the one tends to compare. There's still this, trying to convince part of the community that the machine learning methods are better than physics-based model, which is what the field has been doing for 30 years. And the reality is that physics-based model, at least in this field, are not very good at predicting, because the dynamics is so complex, so nonlinear, and so on. So, for instance, take the case of a 3D MHD that tries to predict solar wind propagation from the sun all the way to Earth. That's very much a boundary condition problem. MHD, it's what it is. It's not much you can do with that, but it's a boundary condition problem where the boundary is kind of unknown. So the way to do is to kind of to infer a proper boundary by images, magnetograms, and then you feed this as your boundary condition to the propagation of a 3D MHD. Reality is that it doesn't work in the sense that the forecast is not very good. Strangely enough, for instance, for the problem of solar wind speed, so the speed of solar wind prediction, like a few hours ahead, the best model is still persistence. If you say the velocity 3 hours ahead is going to be the same velocity as now, it's very hard to beat on average, in an average sense. Yeah.
I think maybe we have time for one question.
Yeah, I got a question here. So I might have missed this in your explanation of your algorithm, but your test set is static, right? That was just from however you split it, and you're iteratively removing stuff from the training set, right?
He might be off mute. We might not be able to hear him.
Okay. Andrew, if you, I'm not entirely sure where in the talk this question came from.
You have your speakers off mute, because I don't think.
Okay. Can't hear me?
Okay, I got you now.
Oh, okay. Yeah. Okay. So this, in the Paris algorithm, right? You're doing these dot products, right, between effectively your vectors between your test and train embedding space, right? And you are iteratively removing examples from that training set, right?
Yes.
Okay. So this kind of strikes me as just maybe another slick way of kind of estimating which examples are noisy or garbage, right? Such that, you can have a better statistical, say, separation to improve your model. My question is, how does that scale? One, when your data set becomes larger, and two, how do you ensure that your test set was indeed maybe even a proper, say, measuring stick, if you can still have these noisy examples in your testing set? Does that kind of make sense?
Yeah, I think, I can understand the question. Switch. So a couple of points. So the way, again, there's a lot of discussion in this for this problem of how to split your training, validation, test. I guess that's the typical experience is that the result very much depend on how you do the splitting, and you want to do it in a proper way. So the way we do here, which I believe is proper, is to separate, to define a storm time, which might be several hours, and separate so that the training set is 98 storms, and we literally do a leave one out exercise. So there's only one storm in your test. So there's no kind of leaking of the data and so on. Now, to answer your first question, I haven't, maybe an exercise I need to do is to sit down and look in the face of those samples that have been thrown away to understand, why. So I don't know whether those are noisy or just they belong to the bulk of the distribution, which is not informative to forecast the rare events. But again, I believe that the statistical distribution of training, validation, and test, it's fairly similar, because of the way we do the splitting. But yeah, about the noise, I don't know. But then again, maybe just to add, even if there's some, I guess that was your point, even if there's some noise in your test, maybe that's not what you're looking for. Again,
right,
the whole point is that the interesting events are the strong storm, which, very large negative DST. And we believe that these are not noisy. If there's some instrumental noise on top of that, it doesn't really shift the distribution so much.
Right. No, I was kind of using noise as just kind of an abstract thing, right? Like in this case, noise could be in fact like an interesting event, right? But if you happen to have that, if such an extreme minority, and if you're not doing, say, multiple splits and running your algorithm on these multiple splits, it's entirely possible that you lose, like the examples you're kicking out are exactly the phenomena you want, right? I'm just trying to figure out, how does that just not either regress to some mean or collapse or introduce any information leakage as you're in your quest to find the right type of training.
So, okay, this goes a little bit into the detail of the algorithm, which I didn't really talk about. Obviously, it's in the paper if you're interested. So the way we do the pruning, because, again, we're interested in the extreme event, we have a validation set. And from this validation set, so I was talking about this matrix S that you build. In fact, we don't really build a matrix. It's just a vector. And we compute these values of S just for the single point that gives the worst score on the validation set. So you have the validation, which is number of storms. There's one point, which possibly is the peak of the storm for which your model doesn't do well. So we focus on improving the score for that one point. So you can be sure that whatever you're pruning, you're throwing away, has nothing to do with that one storm. So it's not you're not throwing away. And then it's principled in the way that we have this delta L. So we know, again, with the assumption that just pruning one point doesn't change everything else, we know that when you prune at one point, delta L improves, becomes more negative, more smaller. So the mean square error, it's better. So that one point was kind of detrimental in the training.
All right, I think we have to head out here and vacate the room, but thank you again for the very nice presentation.
Please take some cookies and juice.